well, maybe I should show one slide first, but right. So this was yesterday in Jeremy's talk, but I mean, like I said, we've seen eigenvalue problems come up many times in the various talks here. So here it's a generalized eigenvalue problem, which of course actually by doing this transformation is turned into a standard eigenvalue problem. And most methods for large eigenvalue problems will do this. I will show, given enough time, I'll show one method that can actually work with the generalized eigenvalue problem form directly. But anyway, so these things come up. And of course in many other problems in science and engineering, eigenvalue problems are very prominent. I mean, so another in computational physics or electronic structure, of course, is the Kohn-Sham problem, where you have to find, you know, all the eigenvalues and eigenstates up to some level, which is actually a very hard problem. But you know, all kinds of engineering, vibrations and so on involve eigenvalue problems too. So first I want to talk a little bit about solvers, and then a little bit about accuracy and sensitivity, which is not, which is complicated. It's not that much. So you often in a standard course you wouldn't see that, but it's very useful in kind of understanding why sometimes your method may not work that well. So, okay, so first a few basics, right? So I'm solving a problem, say ax is equal to lambda x, and what we're going to look at are actually transformations of that problem into a nicer form, right? So if I take an arbitrary non-singular matrix B, then B times A, B inverse is just a change of basis. So you may have seen this before, right? That doesn't change the eigenvalues. Of course it changes the eigenvectors, but you just go from x to B times x, so they change in a very simple way. Okay, so we call this a similarity transformation, and in principle every non-singular B is possible, but it's most stable and accurate to work with orthogonal matrices. So we'll see that actually kind of come up, that in applied mathematics and a lot of engineering, we try to actually come up with basis functions that give relatively well defined problems. They give nice matrices. They're not too ill-conditioned and so on. In fact, but in problems like in physics and chemistry, the problem again is that the problem is so high dimensional that you have to start with, in some sense, tricks. So for example, you want to define your basis function in terms of a set of basis functions that are good approximations to your solution, because then you can keep the space small, which means the amount of work you do is very small. But it may mean that the matrices that you get are ill-conditioned, and so you get numerical problems kind of as a result. So probably in practice you should look for something in the middle. Okay, so in general we will look for an orthogonal similarity transformation. So I'm looking for a unitary or orthogonal matrix Q, depending whether it's complex or real, that looks like Q star AQ, such that, okay, Q star Q is the identity. And I get, well, in the end I want this for, so this is block diagonal in two blocks. In the end, if I want all my eigenvalues, of course I want the size of the blocks to be 1, so I have all my eigenvalues on the diagonal. So I get an upper triangular matrix. But I'm going to focus on problems where A is very large. So in general then you're not interested in all your eigenvalues. You may be interested in some function of the eigenvalues, or you may be interested in some number of them. And it could be small or relatively large, but it's certainly not all of them. And the nice thing is, if I can create a decomposition like this, then the eigenvalues of A are the eigenvalues of L1 and L2. And so kind of to set the notation, in this case we're going to assume that the eigenvalues in L1 are the ones we're interested in, and the ones in L2 are the ones we're not interested in. But they can still bother us in several ways. And of course the other thing is we need to get the eigenvalues that we want into the L1 block, which is small, and then get the rest in the L2 block, which can be large. Well, if A is large and L1 is small, then L2 is large too. So we want to find, right, this orthogonal matrix having kind of two blocks, right? So a Q1 and a Q2 block, such that it gives us this decomposition, where we want the nice part in L1 and the rest in L2. So A times Q1 is Q1 times L1, and then the range of Q1 is an invariant subspace, if you get this, right? And if I find an eigenpair of L1, then that gives me immediately an eigenpair of the matrix as a whole, right? So if L1 times Z is lambda times Z, then A times Q1Z is lambda times Q1Z, right? So this decomposition, so this is the same idea really as what we are saying for these linear systems, right? I build some search space, I project my large problem onto this search space, and then I can solve a small standard problem. So this is the same thing, right? If I would get Q1, And Q2 I don't have to compute. It's just the orthogonal complement of Q1. If I get Q1, then I can project the system on that, and I only have to solve a small eigenvalue problem. And again, so here you would just call, say, a LAPACK some standard routine, right? So you would not worry about solving this problem. So solving this part essentially is a solved problem. You throw it at some subroutine that's high quality and it will give you the answer. Okay, so for large matrices, right, we cannot do full transformations, but at the same time we do not need all the eigenvalues. So we look for a proper basis Q that captures what we're interested in, and we do not need Q2 at all. Okay? So we're looking, and the approximations over this space are simply given by this 1-1 block, Q1 star A Q1, that we saw on the previous slide. Now one thing that is important to ask is, when is an approximation good enough, right? So, okay, so in practice you would like this. You want this residual to be 0. A times Q is Q times L. But you're never going to get this 0. In fact, you're never even going to get it necessarily completely small unless you do a huge amount of work. Now it's important to keep in mind we're always working with approximations, so we must deal with numerical error anyway, so we're not really looking for a 0 here. Now, and of course, one important thing to keep in mind is that it's not just a computer that introduces approximations, right? In many cases, your A may have all kinds of approximations too. So for example, in chemistry, you have some density matrix that is built of all kinds of, electron-electron interactions and electron-electron-electron, three-particle interactions and so on. And they need to compute all of those, and that's actually where most of the work is. And so they don't do this exactly, right? They do those approximately. So your A has all kinds of errors already in there. So that also makes it kind of unnecessary to try to make this overly accurate, because your A is not completely accurate. Okay. So what is a good way of assessing the accuracy? What should you be looking for? Well, so if AQ minus Q1, we can write this again. So this is now the answer we want, right? So is R again is our residual. And if the residual is small relative to A, then in general you would have a good enough answer, right? So what does that mean? Well, okay, so why would I claim that that answer is good enough? So in general, it doesn't necessarily mean that Q or Q1 is very accurate. So that's annoying, right? That's really what you want. You want Q1 to be accurate. But if you have a Q1 that has a very small residual, in general it's useless to try to go on. And the reason is this. So if I would rewrite A as A minus R times Q1, and Q1 has orthonormal columns, right? So the norm of this thing is 1. So the perturbation that I'm introducing here has norm R. So for this matrix, my Q1 L1 eigenpair, or block eigenpair, is exact. So what that means is that the range of Q is an exact invariant subspace of a perturbed matrix A. And so if the norm of R is really small, I just made a very small perturbation of A, and that made this eigenspace exact. So if you assume that A has error in there because of the way you computed it, well, if those errors are larger than the norm of that residual, there's really no difference, right? You cannot distinguish between the A you should have had and the slightly perturbed A. Unless, of course, you would compute your matrix, say, much more accurately. So in general, we call this the backward error, right? So there's a perturbation that makes your computed result exact. So if the backward error is really very small, you have done, in fact, as good as you can expect, right? Because if you don't know your matrix exactly and a small perturbation makes the result exact, there's really nothing else you can do, right? Any more work you're going to do is just going to make more perturbations. And so there's just no way, given the information that you have, to distinguish your computed result from the true result. So if you really need a better Q1, you would have to work in higher precision. So if you're computed your A, making some approximations, then you just have to do better computations there. And that might mean you have to go to higher precision, or you just have to use more accurate rules. If your A partially came out of measurements, well, it just means you have to do your measurements more accurately. But sometimes you can't do that. And so on. Anyway, so this is a good thing to keep in mind, right? So as long as this residual is small relative to A, and of course there's some judgment in there, what is small enough, then Q1 is acceptable. And that doesn't necessarily mean it's particularly accurate. We'll come back to that later on. Okay, so what kind of methods lead to a good Q1? So that's the first question, right? So in many cases, matrices are sparse, and it's possible to do this matrix vector product very cheap. So that's kind of the message we saw for these linear systems too. So let's first consider a very small subspace, right? So this size 1. It's about as small as you can get. And then the method you get, you probably have seen, it's the power method. It works like this. You take an arbitrary initial vector, you multiply by A, and then you normalize it. And you just keep doing that, and the ratio of some arbitrary two components you take as your approximation for your eigenvalue. And under some conditions, if, for example, if you have a stochastic matrix, you can actually show it converges. It has one eigenvalue 1, and all the others are smaller than 1 in magnitude. But it may converge very slowly. And again, this is very similar to, for example, what diffusion Monte Carlo does. Of course, there A is an operator, and you do things in a different way than I'm writing them out here for a matrix, but it's very similar. So why does this work? Well, let A again be diagonalizable. So, okay, you have x, lambda, x inverse. So here x has the eigenvectors in there. And let's assume that lambda 1 is larger in magnitude than all the other eigenvalues. Okay. So you take some arbitrary initial vector and you decompose along the eigenvectors. Now, okay, if alpha 1 here is 0, it won't work in exact arithmetic. In practice, it will still work because after you do this a couple of times, alpha 1 will come in at machine precision because of round off, and then it will blow up nevertheless. So in practice, the algorithm is very robust. But in exact arithmetic, right, you need alpha 1 to be at least non-zero. So what happens if I multiply this by A? If I write it out in this basis, right, I take my xj alpha j and I multiply that by the eigenvalue. And of course, if I do that k times, I get lambda k here. So if I write this as lambda 1k times the rest, so this is the same thing, I just separate out this vector. And of course, I get alpha x1 alpha 1 here, and then all the other components go to 0 because lambda j is smaller in magnitude than lambda 1, right? So that's how the power method works. And okay, and of course you rescale because otherwise this component blows up. But other than that, and of course in the algorithm David described, that what you actually did that somewhat by tuning your reference energy value. So if you make that between lambda 1 and lambda 2, then lambda 1 will blow up and everything else will decay. But in a relative sense, you have this decay anyway. Now, how fast does it converge? Well, so let's assume lambda 1 is larger than lambda 2, which is larger or equal than all the others. Then things will decay at this rate, right? Because this is the relative rate at which your other eigenvectors go to 0. And this can be quite slow. Now, for some, well, in general, for matrix problems, this is often quite slow. So it's not that good. So what can we do to do it better? And actually, I asked David about this, about how this works for some of these electronic structure computations. And there, the nice thing is that you kind of, by constraining the basis to only have wave functions with the right properties, you tend to remove a lot of close-by eigenvalues, right? So you get a matrix that, by construction, has lambda 2 much smaller, well, or at least sufficiently smaller than lambda 1. Now, this is an algorithm that is very basic, so it tends to be taught in simple numerical analysis. But then it's kind of typically said like, well, but nobody really uses this. But now with web search and Google, right, A is so large that most of the other algorithms I'm describing can actually not be done. So actually for things like this, well, of course, nobody knows what Google does now, but we know what they started with, right? Which the PageRank is really a way of constructing a stochastic matrix, and then and then they used variations, or people use variations of the power method, smart variations of the power method, but still working with like one vector, or maybe two to go faster.
Can you explain again what's the relation between Google searches and the matrix you're trying to diagnose?
Oh, okay. So the idea, the PageRank algorithm, I'm not an expert on this, right? But the idea is that you're sitting on an arbitrary web page, and then you pick and then with some probability, you take any of the links on there to jump to the next web page, and then from there you go to the next. At some point you get stuck. So in order to make it a stochastic matrix, they assume that with some residual probability, you go from that page to an arbitrary other page, which of course is quite reasonable because people do that, right? You don't necessarily go from one page to the next. But so that way you actually get a set of walkers very similar to...
So you have an eigenvalue problem you
yeah,
want to solve,
yeah.
is that right?
Yeah, so you have a set of walkers that are going around, and your one stationary...
Equilibrium distribution now, a bunch of random hackers will end up on this page, right?
Yeah, well, not hackers, just websites. Nice consumers looking for commercials. I guess that's really what Google wants, right? Because they based on this. But I mean, so that's what web search does, right? So it's a stochastic matrix. It's based on the same idea of walkers and moving around in some gigantic Markov process, right? Gigantic because there's several billion or maybe a trillion web pages by now. But so yeah, it's actually not that different of a lot of the stuff we've been talking about in this course. And so you make the matrix stochastic, so it has one eigenvalue 1, all the others are smaller, and this equilibrium distribution then is used to actually compute the search, because it's like you're interested, so they have some index about which pages refer to which things, and then based on that they, yeah.
I'd like to clarify this point. So basically, when you diagonalize this matrix, then you get some idea how people keep searching or keep walking around on web pages. So how is it related to advertising? And how is it related to
well, yeah, no. Well, so what you want to find is that how people are interested. Well, so, okay, that's a good question. So you want to find the ranking of web pages. That's really what it does, right? So it wants to distinguish between important pages and less important pages.
Is the probability that you end up
Right,
on a given
right.
page. And then you rank all the pages by that number.
Right.
Right?
And then in addition, you have an index of which pages include which terms. And of course, it's become much smarter. But initially, that was just you scan web pages, you make a collection of the terms, right? So for a while, I guess it's become harder, right? People would, if you wanted to make your web page show up high in Google, you put like search terms in there kind of randomly. So in fact, because it scans the text, right? So you can put text in there that doesn't show up on the page. And then, so if you put in something that is very popular, your page will go up because it, well, not because it's ranked higher, but because it has the terms in there that people might be looking for, even if your page has nothing to do with what they're actually
So in your
doing.
eigenvalue page, you put something about a popular rock star or something.
Exactly, yeah, yeah. And well, that became
But then you
quite
just got to
popular.
get people on your page that
Right.
want to look for that. So.
Exactly, and then I guess you hope that once in a while it happens to be somebody who is interested in eigenvalue problems and will cite your paper or something. So you probably, yeah, you may not want to, you know, maybe you want to take a, I don't know, a jazz musician rather than a rock star. I don't know. Yes.
I mean, I'm looking at this just as a method of getting an eigenvalue. Let's say I'm doing DFT.
Right.
It looks to me like the convergence is now sensitive to the zero of the energy. So let's say, you know, I have my standard set of eigenvalues clustered around 0 or whatever, and then I shift all the energies upwards by a million.
Okay.
Then the ratio of lambda 1 and lambda 2 would be changed. They'd be much nearer to each other.
No, it's e to the minus tau e1 minus e0. So lambda is e in the Hamiltonian that you use, isn't it? E to the minus something.
Well, I don't know exactly about the density, but yeah, if you would shift both lambda 1 and lambda 2, making them much larger, then convergence would be slower. And in fact, like I said, there's smart variations of the power method, and so they try to do the opposite, right? So knowing what you're interested in, they try to shift in such a way that that ratio becomes larger. So that's true. But I don't want to dwell on this too much. Except that the power method has, become back somewhat in favor because some problems are really large. So, okay, how could you improve that? Well, the power method works with one vector. So what if you keep all the vectors, right? So, of course, you're just multiplying by a, so you're back with the Krylov space. And, okay, we can orthogonalize this space. And then, again, I can project my matrix A on Q, so I can represent, well, so the way to think about this is I want to find an approximate eigenvector into the space spanned by the Q vector. So I can write it as Q times W. So now W is my unknown, right? It only has m degrees of freedom, and some eigenvalue mu that I'm interested in. So I want, and I call this a Ritz pair, or this is a Galerkin approximation if I say, well, I want the residual, so AQW minus mu times QW is orthogonal to Q. So if I write that out, because Q is orthogonal, right, I just get Q star AQ times W minus mu times W is 0, right? So now again, I'm back to an m by m eigenvalue problem. So the idea is the same, right? I build a search space, I project on that space, rather than solving, in the previous case, right, we solved an m plus 1 by m least squares problem, so now I solve an m by m, where m is modest, eigenvalue problem. So you can just, again, you throw this at LAPACK, some standard software, and it will give you all the eigenvalues of this small matrix, and you pick the ones that you're interested in. And then you can kind of continue with building up this space, right? So this is a small eigenvalue problem. There's standard methods to solve it. So we find those Ritz pairs from the eigenpairs of this matrix, and the corresponding eigenvector then is A times QW. Okay, so this is the Arnoldi algorithm, and the start is exactly the same as the GMRS algorithm because they build exactly the same orthogonal bases in the same way. Okay, now if we have accurate enough, okay, so now one thing that is different is that for linear systems, this orthogonalization doesn't need to be particularly accurate. So standard modified Gram-Schmid is fine. But for eigenvalue calculations, it needs to be very accurate. So people either do this process twice, or they check the size of this norm, and if it's too small, what happens, right, you start, say, with a unit vector, you orthogonalize everything else, and there's only a tiny vector left. And so that tiny vector is almost noise then, right? It corresponds to, if I took a, well, all right, well, if you have questions about it, ask me later. So then you only reorthogonalize if that happens. So you have a choice there. One is a little bit more efficient than the other. And you get this same decomposition. And so, again, so A is n by n, but this is n by m, so this is smaller, and h is n plus 1 by m. And we take the eigenvalues of the top m by m part. That's really what you do. Now, this is nice, but it's not good enough because, as we discussed, for GMRS, if you do too many steps, right, the cost of this algorithm is no longer really determined by the matrix vector product, but by all the orthogonalizations that you need to do. And the other thing is, if A is really large, if A is now 100 million, and you want to do 1,000 steps, right, you're storing a huge amount of data. So in many ways, too, here, we want to restart in a smart way, and we'll come to that in a moment. Okay, so we compute, but anyway, so after we've done this, right, we compute m approximate eigenpairs by solving this small eigenvalue problem. And then, okay, lambda and then the q and y are the eigenvalues, approximate eigenvalue and eigenvectors of A. They're called Ritz values or Ritz vectors because of the Ritz approximation. So to reduce cost, what we do is we don't just keep making m larger, but we do m steps and then find k approximate eigenvectors. So in many cases, we would be interested in eigenvectors, say, in some region. We may be interested in the lowest energy state. So it would be all the eigenvectors that have the smallest eigenvalues. Or we would be interested in some case in the spectrum in particular range of the complex plane. So we can tune which one we want. Okay, we get the corresponding eigenvectors and discard the rest. So this would be called a dense restart. There's different ways to restart. Some of them are a little bit more elegant. Some of them are a little more stable. So people have, slightly different preferences in what they actually do. The nice thing is all these vectors, if you want to continue, right? So you take k vectors, but they may not be as accurate as you want, so you have to continue anyway. The nice thing is they all have the same residual. So the residual would be the vector that you then use to extend the search space again and find further improvements to your approximation. Right? So if I stick in any eigenvector, so I get A times qy, so okay, by construction that's qm plus 1 h times y. So I can split this matrix in my original h plus this last component, so that was qm plus 1 times E transpose times, okay, the vector y I'm multiplying with, and this is this, m plus 1 m coefficient of the Hessenberg matrix. So this is just a different way of writing H and multiplying. Then I get Q times Y times lambda, so this is my approximate eigenvector times approximate eigenvalue, plus a residual. So if Ym, the last coefficient of this vector, times H is small, so this should be Y, not Ym, is small, then my residual is really small. I can say, okay, this eigenvector is actually accurate. But if it's not, then I may want to continue improving it. But the nice thing is all my eigenvectors, or approximate eigenvectors, have the same residual up to some constant. So I can kind of extend the space, kind of working with the residuals, just with that one vector. Okay. So in some cases, A is symmetric or Hermitian, and so you can do the Lanczos algorithm. And why is that much nicer? Well, so the Lanczos algorithms are Arnoldi applied to a symmetric system. So let's think about applying this Arnoldi recurrence the way we did on the previous slide. So okay, I take a new vector, or I take a vector, I multiply by A, orthogonalize against all the previous ones, normalize and go on. Right, so I get the same thing, but already suggestively I replaced H by T for tridiagonal. Because what's going on is like, well, if A is symmetric, and I look at Q star AQ, this is symmetric too, so T must be symmetric. Now by construction, right, if I orthogonalize my vector against all the previous ones, that gives me an upper triangular part, and then the normalization gives me one subdiagonal. Right, so by construction, T and H are 0 below the subdiagonal. But T is also symmetric, so it must also be 0 above the superdiagonal. Right, so that's clear then that it's tridiagonal. So it means that you have much less work to do. So this annoying cost of half m squared that you get for Arnoldi, you do not have for Lanczos. So for Lanczos, you don't actually have to do any kinds of smart restarts, except for one thing. So in principle, you can just keep going, which for Arnoldi tends to get too expensive. So if you only need eigenvalues, we can just discard the vectors, and restarting is not necessary. Because again, this is an approximate, so Q is not a full matrix, right? So this is an approximate similarity transformation. So the eigenvalues of T converge to the eigenvalues of A. And there's ways to check that. So if we don't need the vectors, we don't need to restart. Now, if we do need the vectors, then we can throw the basis vectors away because we need them to construct the eigenvectors. But there's other tricks there too. So we'll see later on that once you have an eigenvalue, so if you can get an accurate eigenvalue from T at some point, and you didn't keep the vectors, you want to compute the eigenvector, it turns out in a few slides that you can find that very efficiently as long as you can, A is not so large that you can do an iterative solve or a direct solve. So if you can factorize A, so because eigenvalue problems are harder than linear systems, right, large is also somewhat different. So if you have like a, say, 100,000 by 100,000 eigenvalue problem, it's pretty large, but you could still solve a linear system for that matrix A pretty easily unless it's quite dense. Anyway, we'll come back to that in a moment. Okay, if you do not restart and you throw the vectors away, you have to, well, in any case, with Lanczos, if you exploit the fact that it's tridiagonal, so you do not do a full orthogonalization, the vectors they lose orthogonality. They're not, in exact arithmetic they would all be orthogonal, but in practice they're not, and what that gives you are spurious copies of the eigenvalues. So that's something then you need to filter out later. But otherwise, techniques for Arnoldi can be used. So if we do Arnoldi, okay, we need to restart from time to time to save memory and CPU time. And this is the same for Lanczos if we want to compute the eigenvectors or we orthogonalize for accuracy. So an efficient and accurate way to do this is called implicitly restarted Arnoldi. And if you know the ARPAC, that's essentially what ARPAC is based on. So ARPAC was developed by Dennis Sorensen. The method was developed by Dennis Sorensen, and then several of his students kind of, helped develop the package. So Rich LeHouk, Chao Yang, and one more student whose name escapes me right now were involved in that. And ARPAC has essentially been absorbed, I think, in Trilinos. So it's a large package of solvers and all kinds of numerical software that's produced by Sandia National Labs, and you can download it from their website. So the basic idea is, I mentioned this idea of truncating, right? So you do m steps, you find the k eigenvalues and eigenvectors you're interested in, you throw everything else away, and then you kind of keep on extending the basis using this residual. So this is just a very elegant way, in some sense, of doing that. Okay, so the method discards unwanted Ritz pairs using a polynomial filter applied to this Hessenberg matrix, which is this small matrix, the m plus 1 by m matrix. And there's slightly different things you can do. So you can really discard unwanted eigenpairs, and I think that's the standard thing that ARPAC does. You can also, rather than discard them, you can just dampen them very strongly, and that has some advantage in some cases. So the remaining vectors span a new Krylov space with a different starting vector, and that starting vector is just a polynomial applied to the original vector in such a way that, okay, it has large components in the spectrum that you want and small components in the part that you don't want, right? So you get essentially a new starting vector implicitly with the next k steps already, and then you build it out to another m, you apply the same trick, and so on. And so so Arnoldi is not necessarily always the best method for the problem, but this is probably by far the most mature software that is around. So it's become very popular, right, because it's really high quality software. All right. Now, okay, so we went from the power method that may converge slowly to the Arnoldi method, and that can converge much faster because you can use polynomials, the same we kind of described for solving linear systems, but it may still not be very fast, especially if you have this case that you want an eigenvalue in the middle of a bunch of other eigenvalues. There's no good polynomial, right? So what can you do then? So here's a smart idea, which is quite old. So what if we want the smallest eigenvalue, any one that's not the largest in magnitude, right? Well, so you can do the opposite in some sense of power iteration. You can do inverse iteration. You just do the power method with A inverse. Of course, this means that you need to have A inverse, computable reasonably efficiently. So if A is very large or say a direct LU factorization is not very cheap. This may not be so practical, but there are variations of this that work very well that I'll show in a moment. And then if you do this, you can do another smart trick that is really very useful. So you can say, let's not do it for A, but let's do it for A minus S times the identity. So what does A minus S times the identity do? It shifts all the eigenvalues by S. That's really all it does. So what happens is, suppose you know your incident eigenvalues in a certain region. So you say you pick the middle of that region, you make that your S, you shift them. So now all of the eigenvalues that you're interested in are very close to 0. And so in the inverse, that means they go to infinity. So this is a nifty way. It's not cheap, right, because you need to compute an inverse, but it's an easy way to make the eigenvalues that you're interested in very, very large compared to the others. And then the power method will converge very rapidly. So like I said, if you would do Lanczos, and throw the vectors away, just looking for eigenvalues, if you can factorize A, and you know which eigenvalue you're looking for, right, so now S is very, very accurate for a specific eigenvalue, this will converge in like 1 or 2 steps. Right? So once you have the eigenvalue, if you can factorize A, you can find the eigenvector very quickly. The other thing is, and this has become very popular in methods that I'll mention in a moment, which are called shift and approximate invert. Shift invert they're typically called, which is what this does, but I mean they're really doing approximate invert. Become very popular, is that you may not know what S is, the eigenvalue that you're after. You may know I want the one closest to 0, but you don't know what it is, right? So you don't know S exactly, but you can improve it as you go. And one of the most, again, a well-known algorithm that's on the next slide is Rayleigh quotient iteration. Right? Anyway, so this is how it works. And the nice thing is, okay, by making S close to J, right, you can make this ratio very large. And then convergence, or small, and if you incident lambda k. You can make this ratio really small. So in principle, by picking S close enough to lambda k, if you know it, or as you kind of discover it, you can make the algorithm converge arbitrarily fast. So this is the idea behind Rayleigh quotient iteration. So let X be an approximate eigenvector. Should have made this a little larger, I'm sorry. Let X be an approximate eigenvector for a real matrix A, then approximating the eigenvalue is given by an n by 1 linear least squares problem. So this is what defines the Rayleigh quotient, right? So if I say X times lambda hat is approximately AX, I solve the least squares problem. Usually you'd solve it the other way around, right? Multiply by X transpose, I get that lambda looks like this. So, and this kind of holds quite generally, and if you make it into a matrix, you make it orthonormal, that's the best approximation to the eigenvalue you can get. So once I have an approximate eigenvector, I can actually get a good approximation to the eigenvalue. And in fact, we saw this, again, this is very similar to what you saw yesterday. When you look at the ground state and you do a perturbation of the energy, you do a perturbation of the wave function, that's really just a perturbation of the eigenvector. You take that perturbation, you can always take that orthogonal, you write everything out, and you see that the approximation to the eigenvalue, in this case the ground state energy, is quadratic. Right? So that's the same thing here. You see a lot of the same things are coming back. So you can write this out in this component too, right? So you can write this out exactly, and you see that if you perturb the eigenvector by some epsilon, you get the eigenvalue accurate to epsilon squared. So this is kind of nice, because if you now improve the eigenvalue estimate every time, so if you have a reasonably accurate eigenvector, right, your eigenvalue is very accurate. But we saw that for inverse iteration, if you make your shift really accurate, you converge very fast. So you can kind of do this, and then you can work out, you can look up the slides, you can work out that the convergence for a symmetric matrix is cubic. Right? So you didn't think that Newton is fast. So here if you have 2 digits of accuracy, the next step you'll have 6 and then 18 and so on, right? So convergence is extremely rapid. It has a drawback, of course, because it means you have to solve this linear system, and S changes at every step. So in practice, people, if you can factorize relatively cheaply compared to solving an eigenvalue problem, this is useful. But in practice, you may not want to, there is a cost involved there. Now, there's some things you can do. So in many cases, what you can do is, it's not that expensive to reduce A to tridiagonal form. So you find a Q, the Q you're after, right, would be such that Q star AQ is diagonal. That's actually really hard. But finding a Q such that Q transpose AQ is tridiagonal is relatively easy. There's a fixed fixed algorithm to do that. And the nice thing then, of course, is factorizing a tridiagonal matrix is extremely cheap. So that's order n work. So it turns out, right, in some variation you could say that algorithms that solve dense eigenvalue problems are based on this idea. You do this transformation first, and if you look at the cost that LAPEX says for solving an m by m is some small for a small dense matrix, is really the cost of this thing, because everything else after that is very, very fast and almost free of cost. All right, what if A is so large that you don't want to compute this factorization, right? So if A is very large, you can do that. So then you can do inverse iteration with a shift, but you do the inverse approximately, right? So hence they're approximate shift invert methods, or shift approximate invert would be a better name, right? So you approximate the solution by one step approximation or a few steps of an iterative method. Then you get a better approximation to your eigenvalue, you update your eigenvalue that you stick in there, and you do another shift with an approximate invert. And so two very popular methods, Davidson's method in chemistry and the Jacobi-Davidson method that was kind of based on that with some correction. So Davidson's method, if your matrix is very strongly diagonally dominant, converges very rapidly. You don't have to do that much else. But in more general matrices, you may not have that, and then by maintaining some explicit orthogonality and using a search space, Jacobi-Davidson is somewhat better. Although chemists that are happy with Davidson will not really bother with that. Okay, so here's the idea, right? It also uses a search space and Ritz values, but extension of the search space is different. It's not just the matrix vector product. So let's say you have some Q that has orthogonal columns, and Q star AQ is H. So you can find the eigenvalues, and let's say you're interested in a particular pair, y and lambda. So in many cases, right, again, you're looking for the lowest energy, so you just pick the lambda with the smallest lambda here. And then you would extend the search space. You solve a certain correction equation. You take the diagonal of A, which of course if A is strongly diagonally dominant is a reasonable approximation to A, minus lambda I. So this is kind of shift invert, except that you replaced A by just its diagonal. And then you get a solution, and you put that back into the search space. You project on that space, and so on. And the idea is that this is an approximation to the correction that you need to solve for. So T is like complements your approximate eigenvector. So it's essentially a Newton-type iteration, really. All right. So this is effective for the outermost eigenvalues, and especially if the matrix is strongly diagonally dominant. And, well, okay. And okay, so there's various papers that have been written about why this method works really well, but it's kind of somewhat together with the kind of problems that Davidson was really looking at. So it's very good for some classes of problems, but not necessarily good for general problems. But the idea can be generalized, and so that brought about the Jacobi-Davidson method, which was by Slijpen and van der Voort. So Davidson's method came from Davidson, obviously. So there's a few variations. Again, so we're interested in this problem. Let's say you already have some basis. Of course, typically would start with an arbitrary vector again, unless you have a good approximation to your eigenvector, then you can start with that. So you compute this reduction to a k by k matrix, and you find its eigenvalues. And let's say there's, again, you know which region of the eigenvalues or which eigenvalues you're interested in. So you pick some Ritz pair. And now, rather than solve with, okay, so in the previous slide, right, we took the diagonal of A minus lambda times T equals minus R. So there's two changes. We replaced the diagonal just by A itself again. So we used really the whole matrix. It's because, if your matrix is not necessarily strongly diagonally dominant, the diagonal is not a good approximation. And in addition, we apply one other trick. So we project the eigenvalue vector that we have out of the whole system, right? So effectively, we work on an n-1 dimensional space here rather than an n-dimensional space to solve for T. And the reason is that once L would be and U would be quite accurate, your T that you would find if you didn't do this projection would be very close to U. So essentially, it would not be very useful. Right now, you can orthogonalize it, but again, if you take a vector that's very close to another vector, you orthogonalize it, you essentially end up with noise. So the extension wouldn't be really useful. So instead of kind of solving and then orthogonalizing, you maintain this specific orthogonality right in the system that you're solving. Okay. And then, okay, if you solve for t, then you orthogonalize it against the previous q vectors and you essentially add it to the basis. And you can continue. And okay, at some point, of course, this gets large as well, so you may want to truncate it down. And you can do the same thing. You can use some, you can find the eigenvalues and throw the ones you're not interested in away. There's other things you can do. So one popular way is computing a partial surety composition explicitly and kind of chop with the eigenvalues that you're interested in at the top, so to speak, and then discarding the remainder. Now, why is this really nice? So it's a Newton-type method. And so if lambda and u are fairly accurate, it will converge pretty quickly. Even if you didn't use the search space, right? If you're close enough, it will converge quadratically. If you solve this linear system exactly, but you don't want to do that. But the other nice thing is, okay, the way you extend this search space is by a linear solve. And we know how to do that very well. So, for example, you can also find a preconditioner for this system, and then, okay, you have to solve slightly different systems, so you may want to update your preconditioner as well. But so you can throw a lot of extra, so if you want to solve this accurately, right, if you can precondition it, then you can solve these systems fairly accurately and you get pretty fast convergence. Okay? So and that's made this method quite popular. And then so this is the original paper. And then, so Ronald Morgan did a lot of work on Davidson's method. So you can find some more information about that as well. And then 2 also provides a lot of reference in general to eigenvalue problems. And actually there's, on another, when I go to my next set of slides, I definitely. There's also 1 or 2 good books that I then mentioned. Okay, maybe one quick comparison, right? So what should you use? Well, I mean, really, if you really want to know, you probably should take your problem, try out some of these methods, and figure out which works best. But like a very quick comparison, I would say that implicitly we started Arnoldi and Davidson work really well for eigenvalues on the boundary of the spectrum. And of course, by shifting the system, again, doing some shift invert, if you can factorize A, you can put almost anything on the boundary of the spectrum of your shifted matrix.
So that means the lowest ground state. Is that what you mean?
Yeah, in general, or in some cases, you're interested in the largest eigenvalue. That's on the outside too. Yeah. And if your eigenvalues are just some region in the complex plane, then the outside, right, could be. But if you want something in the middle, they tend to be less effective. And Jacobi-Davidson, because it's a more effective kind of shift approximate invert method, is actually very good at that. It's not bad for the others, but I think if you're looking on the outside of the spectrum, then it's probably less necessary to use this method. So I would say it's superior for interior eigenvalue problems. Now there's a few other things, and that is that since it's a Newton-type method, it tends to zoom in on an eigenvalue or eigenpair very quickly. And that is if you really want many eigenvalues. In Jacobi-Davidson, what you would typically do is you find one and then you kind of shift your target, so to speak. You find the next and next and next. And so if you want many, then IRA has some advantage in that it's much better at looking at many eigenvalues at once because you just tune the space to cover a whole range of eigenvalues. And it doesn't zoom in necessarily on any one in particular. So those are some very quick considerations to decide maybe which one you want to use. All right, that's it.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.